I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me for this video where we are examining this very interesting indefinite integral e exponent 2x minus 1 divided by e exponent 2x plus 1 dx. You can essentially arrive at your antiderivative very easily if you think about a variety of algebraic techniques with which you can work your way backwards or reverse your way to the antiderivative. Look here at the numerator, I have e exponent 2x minus 1, but algebraically it's coming from e exponent x minus 1 over e exponent x. Think about it. If you do a common denominator over here, it's e exponent x, then I have e exponent 2x minus 1. Yes, you don't see the denominator e exponent x over here, but imagine it's there, but it will disappear. This right here is from the numerator, and look how it played out. Look here at the denominator, e exponent 2x plus 1 is coming from e exponent x plus 1 over e exponent x. And now what I'm really looking at is e exponent 2x, because when you do the algebra over here, you have e exponent 2x plus 1 divided by e exponent x. Again, this denominator shows up. But if you were to take the quotient of these two items, you can see the denominators cancelled out. So it's telling you you're looking at something which is of this form right over here in the numerator and in the denominator. You can rewrite these by moving these exponents up. In essence, I have e exponent x minus e exponent minus x in the numerator, and then looking here in the denominator, I have e exponent x plus e exponent minus x. Now imagine if both of these had a hidden 2 or even an actual 2, but the 2's cancel out because you're doing a quotient of everything all along. Now in essence, you're looking here at a hyperbolic sign in the numerator as a function, then you're looking at a hyperbolic cosine in the denominator, and that's exactly what you have. Hyperbolic sine divided by hyperbolic cosine, and you are looking at that as your integral, and this becomes your integral, which represents what you have here. But again, we've used algebraic techniques to represent it in this way, and you could technically work from here backwards and arrive all the way over here. And you can just do the algebra, start from right over here, send it through the algebraic techniques, and you'll end up right over here. So this represents exactly what you have over here, and it's represented equally well with this. So now all we have to do is integrate that. A good u substitution will carry you through to the end much faster than a poor u substitution. What's a good u substitution? Look right here. U is equal to hyperbolic cosine x. Why is this a good substitution? Because when you do the derivative, here you have hyperbolic sine x dx. This item over here can be represented exactly with the du and the denominator with this. So you are in essence looking at a du divided by u. The du in the numerator and the u in the denominator, which you know is 1 over u du, which you know is the natural log u plus c. When you resubstitute your u right over here, you're looking here as your antiderivative natural log of hyperbolic cosine x plus c. And this right here is your antiderivative, and it's certified. It should be good. Again, we worked our way backwards using algebraic techniques. We had a vision of what it could be, and we worked it backwards to arrive at that vision, which was hyperbolic sine divided by hyperbolic cosine, and we easily come to our antiderivative. Well, have a good day and thank you for watching.